Today's point is electric potential difference. We have seen that what is exactly the electric potential energy. Electric potential energy means that the assembly of charges which bring from infinity to the present location. And for that, the work done is there, or work done is necessary to bring that charge assembly to their present location from the infinity. That is called electric potential energy. Now, we are considering here the electric potential difference. Here also, we have to mention the test charge. And test charge is at infinite distance. And to bring that point of that test charge from infinite distance to the present location, so the energy must be needed or work done is needed there. When a charge is moving from one point to another in an electric field, we need to do work against the force due to electric field. We have seen that. From any point to other point, for the reason one point or one charge is moving from one point to another point. For that reason, the work is done. Work done is necessary to do that work, and this work done is called electric potential energy. We have already seen that. And this work done is called electric potential energy. We have already stated. As the force is proportional to charge, we know that force is proportional to charge or the product of charge. We have seen. Now, as because of force is directly proportional to the charge, that means to say that work is also directly proportional to the charge. That means work is dependent on the charge. We say, but the work done is thought to be independent, the path taken to move charge from first point to the other. But we know that, we mentioned that as the force dependent on the charge, or force is directly proportional to the charge. We can say force is dependent on charge, as the force is dependent on charge, so work done is also depends on the charge. Work done is also dependent upon the charge. But here we have to mention that the path along which the positive charge go from one place to another place, that in that case the path is independent of the work. The path is independent of the work. Let the work done is moving the charge Q naught from point B to A. We say that work done is said to be WdA. That means to say that for moving a test charge Q naught from point B to A, there is a work done, and that work done can be written as WdA. Since the potential or positive work is done, due to move the charge from B to A, that means to say that what we say here is point B and here point A. That means that point B is or charge, this charge Q naught is moving to the point A, and so that we can say that for that movement the work is done, and that work done can be written as WdA. That means charge is transferring from point B to point A. That's it. The energy stored is greater than A than that of B. Here, the energy stored is greater than that of the point B. The energy stored at that point is said to be greater than that point B. The electric potential difference between point A and B, that is we write as WBA. That is said to be electric potential difference. Now we know that here point A, what is that? The energy stored at that point is greater than that point B. That means to say that there is energy difference. There is energy difference. So that energy difference is said to be electrical potential difference, or electric potential difference, that is WPA equals, or WPA, therefore WPA upon Q naught, and it is equal to constant, and it is equal to constant. WPA upon Q naught equals to constant, and that constant is nothing but our potential difference. That is said to be potential difference, that is VAB equals WBA upon Q naught. VAB, that constant is also called as potential difference, electric potential difference. The let V be the electric potential point B and VA be the electric potential at point B. Suppose here at point B, what we have taken as a point charge or test charge Q naught, and we allowed that test charge Q naught to move from point B to point A. Here, on that moment, the energy stored at that particular point A is greater than energy stored at point B. So there is an energy difference. And you know that WPA upon Q naught equals to constant, and that the constant is nothing but potential difference. That potential difference between point AB. That means the potential point for B is VB, and the electric potential at point A is said to be VA. Therefore, instead of VBA by AB, we can write as VA minus VB equals W V due to A divided by naught. Here, for that we can write VA minus VB equals to WBA upon naught. This is the electric potential difference. Hence, the electric potential meaningful with respect to the reference point. Here, we know that electric potential is, or electric potential difference, or electric potential is meaningful only with the reference point. Only with the reference point. So we have done that. VAB equals to WBA upon Q naught. VA minus VB equals to WBA upon Q naught. Now, we have to take another example. It is said to be electric potential difference, and now we have to calculate the electric potential difference due to electric dipole. Electric potential difference due to electric dipole. Here, electric potential due to a point charge, that is said to be VR minus V reference equal to work done for bringing the charge Q naught from infinity to the present location. That means to say that to point reference point R upon Q naught. Work done in bringing test charge from infinity to our reference point R divided by naught. So VR minus of V reference equal to W R reference, or you can say that VA upon naught. It is also there. Conventionally, the absolute electric potential at any point at distance R is defined by taking the reference point at infinity. So we have to take that reference point at infinity. That means from infinity. Earlier we stated like VA minus VB. Here the point is VB as reference point. It is considered it is at infinity. And to bring that point charge or test charge from infinity to the present point, here we taken as R is our reference point. So for bringing that work is done, that work upon test charge, it is nothing but electric field intensity, or you can say that electric potential at point P. Electric potential at point in electric field is defined as, we have to mention, it is said to be electric potential. electric potential at a point in electric field. Electric potential at a point in electric field is defined as the amount of work done. The amount of work done to bring unit positive charge from infinity to that point against the direction of electric field intensity or electric intensity. We are defining electric intensity at a point in the electric field or in the electric field. It is defined as the amount of work done to bring the unit positive charge from infinity to that point against the direction of electric field intensity. Here we can say that V general V equals W upon Q naught. Here it is electric potential, it is the work done for bringing that point charge or rotation from infinity to the present location upon Q naught. It is said to be electric potential. Here, phi is the electric potential. The SI unit of electric potential is joule per coulomb, or it is named as volt. We have seen at 10 the electric potential always measured in volt, and volt is nothing but joule per coulomb. The dimensions are L raised to 2, M raised to 1, T raised to minus 3 and R raised to minus 1. These are the dimensions of the electric potential. So, we know that the joule per coulomb is said to be volt. Now, in case of defining 1 volt, that means to say that when will be the value of potential 1 volt? 1 volt is equal to 1 joule. 1 joule upon 1 coulomb. Here it is the definition for 1 volt. That means to say that the work done, 1 joule of energy is required to do the work to bring that 1 coulomb of charge from infinity to the present reference point, and when the electric potential is there, that electric potential is said to be 1 volt. Electric potential depends on following things. We already know that electric potential depends on the position of the field point in the electric, or position of the point in the electric field, where exact the reference point is situated at that particular field. So that electric potential is dependent on the position of the point in the electric field and the medium. And the second one is medium. Electric potential may be positive or negative depending upon the nature of charge. Electric potential may be positive, may be negative. It is depending upon the what kind of nature of that particular charge has. Now, for our consideration, suppose this is said to be point O, this is said to be point, this is said to be point E, it is M, and it is M. It represents the direction of electric field. This distance is taken as R, this distance is taken as dx, this is said to be total x, here minus q, here plus q, or q naught is placed at point M. This point is said to be A. The distance from O to M is taken as x. Exactly, O to M is taken as x. So, consider a point A at distance R from point O. A is a point, it is at the distance of R from point O. The dielectric medium of constant K, consider a charge Q naught at infinity from the charge Q. When the test charge is at M, experiences the force which is given by. Now, look here. Here we are talking about, suppose that is plus q, and from that charge plus q or point O, the q naught is very far, or it is said to be it is placed at the infinity, and we have to bring that charge from infinity to present location. Our present location is at point A. So here we know that the distance of OA is said to be R, the distance of element is said to be small distance, small element dx, and from O to M it is taken as x, the distance between them is x. So it experiences the test charge which is placed at point O naught. It experiences such kind of force due to field, and that force is given as F equals 1 upon 4 pi epsilon 0 k into q naught upon x square. Q naught upon x square. It is along OA. This is the value of force, the experience of that force. F equals to 1 upon 4 pi epsilon 0 into q naught upon x square. It is along the direction of OA. So we know that dW is the smallest work done to bring that point charge from M to N. So we required dW small work done equals to minus F times dx. We know that force into displacement is nothing but work done. Force into displacement is nothing but work done, and we have the value of force. So we can write as dW equals 1 upon 4 pi epsilon 0 k into q naught upon x square into dx. But it is said to be the smallest work done, and we have to integrate for getting all total work done. And for getting total work done, we have to take integration. Total work done is equal to integration of dW. It is x equal to infinity, and here the point R. We say, therefore, we have integration from x equal to infinity to R. Value of dW is nothing but 1 upon 4 pi epsilon 0 k into q naught upon x square into dx. For the sake of calculation, our convenience, we take it as a constant. So W equals 1 or q naught upon 4 pi epsilon 0 k into integration of from x equal to infinity to R. We write as 1 upon x square into dx. Again, W equals total work done equals q naught divided by 4 pi epsilon 0 k integration x equal to infinity to R, that x bring towards it becomes x raised to minus 2 into dx, and after solving that integration we get W equals q naught upon 4 pi epsilon 0 k. Here we write as x raised to minus 2 plus 1 divided by minus 2 plus 1 from x equal to infinity to R. After solving this, we have W equals to q naught divided by 4 pi epsilon 0 k. Here minus 2 plus 1, it becomes x raised to minus 1 upon minus 1 raised to x equal to infinity to R. Again we have W equals q naught upon 4 pi epsilon 0 k into x raised to minus 1 from x equal to infinity to R. and again W equals to Q upon Q into Q naught upon 4 pi epsilon 0 K into 1 upon X. So X equal to infinity to R, and that X is equal to R, so we get W equals to Q naught upon 4 pi epsilon 0 K into 1 upon R. Here we can easily say that W equals to 1 upon 4 pi epsilon 0 K into Q naught upon R. Now again we have here, we know that pole potential, electric potential work done upon Q naught. So P equals to, what is the value of work done? That value of work done 1 upon 4 pi epsilon 0 K into, instead of the, you can write Q naught upon Q naught into R, so Q naught get cancelled, so finally we get the value of 1 upon 4 pi epsilon 0 K into 1 upon R. This is the value for electric potential due to point charge. This is the value of electric potential due to point charge. This is for calculating the electric potential due to a point charge. So we have seen that, what is that value. Finally we get, that is P 1 upon 4 pi epsilon 0 K into 1 upon R. Electric potential at the point due to point charge is inversely proportional to distance. From this equation we can say that. And the potential due to positive charge is positive, while the potential due to negative charge is negative. Electric potential here we take it as a positive. It is positive due to positive charge. And if you take the negative charge, it is negative due to negative charge. If this term taking constant, we can say that V is proportional to or inversely proportional to the R. Right? That means to say that the electric potential due to point charge is inversely proportional to its distance. Inversely proportional to its distance. Here we have seen that point. Now the next point is that the electric field intensity at point in the electric field is equal to the negative rate change of potential with respect to distance. Suppose we take a relation, in order to get relation between electric potential and intensity. That is, suppose relation between electric field and intensity, we know that F equals to E times, F equal to E times Q naught. That is, we obtain from the value of electric intensity equal to F upon Q naught. And from that value, it is the value of intensity. We taken as it is as a magnitude E equals to F upon Q naught. And from this equation, we have that equation F equals to F equal to E times Q naught here. dW is nothing but small work done. dW equals to minus of F into dx. Here negative sign, force and displacement are always in the opposite direction. The negative sign indicates that force and displacements are always in opposite direction. So here we get F equals to E times Q naught and dW. So again we know that something F into dx. So dV equals to minus E times dx. So it becomes E equals to minus dV by dx. That means it is the electric intensity is negative of rate of change of electric potential upon the change is the work done is work done per unit charge. The work done per unit charge displaced is inversely or inverse of potential dV. That is, dV is small change in potential dV is small change in potential over the distance dx. It is said to be small difference in potential. It is in the small difference in the distance, or we can say that distance dx, and that quantity dv upon dx. Here, this quantity is very much important. Or simply dv by dx. This quantity is very much important because this quantity gives the value of potential gradient. It represents the rate of change of potential with respect to distance in the direction of intensity. It is called as potential gradient. It is rate of change of potential to the displacement, or the ratio of electric potential to the distance. This ratio is nothing but is called as the electric potential gradient, or simply we can say that it is said to be potential gradient. Again, it is called in equation. This equation, the negative sign shows that the potential decreases with distance measured in the direction of electric field. It is the distance measured in the direction of electric field that represent from that equation. The electric field intensity at a point in the electric field is equal to the negative rate of change of potential with respect to distance at a point measured in the direction of electric intensity. Therefore, from this equation, we easily say that it is the rate of change of negative electric potential with respect to the displacement or distance. So, in case of experimental surface electric field, we can say that, or this term is said to be potential gradient. This term is said to be potential gradient. The electric potential gradient or potential gradient, the unit is volt per meter. We can measure because the electric potential gradient or potential gradient is nothing but dV by dx. So the unit potential is measured in volt, and volt per meter. Volt per meter is the SI unit of potential gradient. So, in case of equipotential surface, electric field is any point is always normal. Note that it is found that work done does not depend upon the path chosen moving per test charge from point B to point A against the direction of field intensity. We have seen that. We see that the work done is perfectly depending upon the charge. The work done is not dependent upon the path, that path which acquired by the test charge from moving from point B to A. Second, the surface passing through all the points in same potential in electric field is called equipotential surface. Hence, work is done in moving charge on no work is done in moving charge on equipotential surface. If any surface which has equal potential at the same point, and that surface is said to be equipotential surface. And in case of on the surface of equipotential surface, there is no work done from moving charge from one place to another place, because that surface is said to be equally potential. It has equal potential. Surface of sphere with charge at the center. Suppose what is the equipotential surface? The any type of, or suppose we take as the sphere, and sphere has some charges at the center, and these charges are said to be at the same potential level. That means they are said to be